Today we're looking at 3.3, the unit circle and circular functions. So remember what the unit circle is. It's just a circle that has a radius of 1. So we refer to that as the unit circle, okay? And it could be whatever unit you want. We're just saying 1 unit is my radius, okay? So therefore I have a unit circle. Do you remember from, oh gosh, when might you have seen this? Certainly in geometry, area of a circle. I mean, not area of a circle. Equation of a circle in the coordinate plane. X squared plus y squared equals r squared. Do you remember that? So for any circle, you have x squared plus y squared equals r squared. As long as your vertex is at the origin. So if I have my unit circle and I put the origin, the center of my circle at the origin, and my radius is 1, x squared plus y squared equals 1 is going to represent my unit circle. So, do you remember seeing this in geometry? X squared plus y squared equals r squared? Does that kind of sound familiar somewhere in there?
Yeah.
Well, there it is. So, if I asked you to give me the equation of a circle whose center was at the origin with a radius of 5, it would just be x squared plus y squared equals 25. That's it. That's as hard as it gets with circles. So it's just, as long as the center is at the origin, you're just going to do your radius squared. So, what if the radius was square root of 3? It would be x squared plus y squared equals?
9.
If it's square root of 3? Is the length of the radius?
3.
Now it would be 3, right? Any hoosers, we're dealing with a unit circle. Our radius is always 1. 1 squared is always 1. So it's nice and easy. So we're going to be using this formula here. We still have S equals R theta, right? Our formula that we learned in the other section. Now, I don't know if you remember this or not, but do you remember way back in chapter 1 when we were looking at these things and we had like sine was equal to y over r, and we were making the triangle and we had y over r. Remember that? Yeah. So now we're still doing this, but since the radius is always 1, r is always 1 for these. So instead of saying sine of theta equals y over r, I can just say sine of theta equals y. Because r is just 1. Right? Right? So if I just divide by 1, I don't even need to put divide by r at all. So that's what you're going to see here with these circular functions. So instead of saying sine of s equals y over r, I can just say that it's equal to y in my unit circle. Cosine of s, I do the same thing. Cosine of s, if we look here, it was normally x over r on our reference sheet. But if r is just 1, cosine is just going to be equal to x. Tangent's a little bit different because that one didn't have r in it at all. So that one's just going to stay y over x.
Does S still just as a double around the outside of the circle? Or is that a different S?
Yeah, no, same thing. So cosecant still is the reciprocal of sine. So the reciprocal of y would be 1 over y. Secant, reciprocal of cosine, so this is going to be 1 over x. And then cotangent, reciprocal of tangent, x over y. Okay, now we have to talk a little bit about these because I have some fractions here. What am I never allowed to have in a fraction? In the denominator? 0. I can't have 0 in the denominator. So I can't have x being equal to 0 for the tangent. Otherwise I'm going to get an undefined expression. So same thing for cotangent, y can't be 0. Not allowed to have zeros in those denominators. Same thing over here, x can't be 0 and y can't be 0. Okay, so here's basically what we're going to be doing. You're going to have some angle, some value of theta, right? I don't know, let's just say it's this. You're going to have some value of theta, and we're going to try and locate where is that on the coordinate plane? Like, what's that ordered pair? And how can we do that? Well, ladies and gentlemen, I'm just going to use sine and cosine. Look, sine of s is equal to y, and cosine of s is equal to x. So as long as I know what s is, right, and s is equal to r theta, and r is just 1, so it's really s and theta are the same thing. So all I have to do is figure out the cosine and the sine, and that'll get me that ordered pair. You with me? Maybe a little bit? So that'll get me some ordered pair x and y, but to get that x, I'm just going to do cosine of s. And to get that y, I'm just going to do sine of s. And if you want to remind yourself, s is equal to theta because s equals r theta, and r is 1. So you could also say cosine theta, sine of theta, because s and theta, same thing here. All right, are we okay so far? This gets a little weird, so I just want to make sure that we're digesting before I throw too much more at you. We're okay? Everybody's okay? Yeah? All right, good. So now let's talk about domains of circular functions. Domain. What's domain again? If I ask you the bottom, domain is all the x values that you can plug in and actually get an answer. So for example, I'm trying to see if I have a nice graph here somewhere. Of course I don't. I'll make one. Say you graphed a parabola and it looked like this. Right? The domain. It's all the x values that this graph will cover. Will this graph cover every x value in the whole wide world? Yeah, eventually. It's going to keep going out, going to keep going out. Range was your y values. Will I get every y value out in the whole wide world? Yeah, it stops right here. You'll never get a y value down here for this function. They're all going to be here or higher. Right. So that's just reminding you about domain and range. Domain is all your x values. What x values can I plug in and actually get an answer back out? Range is what y values will I get out when you plug in whatever you're plugging in for the domain. All right, so anywho, sine and cosine. Any s you plug in will have an ordered pair, x comma y, associated with it. So, domain of sine and cosine is negative infinity to positive infinity. Basically, I can plug in anything I want for sine and cosine. In other words, like anywhere I stop along the circle will have a sine and cosine value. I'm never going to get something that's undefined for sine and cosine. Ooh, that's a good tip. Am I going to have the same thing with tangent? and secant. Let's look at tangent and secant. What do you notice about tangent and secant?
They can't.
They both can't have x's that are equal to 0. So I cannot plug in an x equal to 0.
That's not infinity.
Correct. All right, so for tangent and secant, let's see, how can I fit all this in?
Nowhere.
I'm going to do it,
Make it less than that. It's just like
I'll do it here. Both have x in denominator. So x can't equal 0. But where does x equal 0? And remember, x is cosine. So cosine is equal to 0 at, the first time it happens is at 90 degrees. 90 degrees, which is pi over 2. It also happens at 270, which is 3 pi over 2. And then you could keep going forever. So it's every iteration of 100 and of 90 and 270 is going to hit an x equal to 0. So if you want a few more examples, 450 degrees, which is 5 pi over 2, and 630, and you could keep going forever. That would be 7 pi over 2. Are you noticing a pattern with these radians? Look what I have. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Could you guess the next one? 9 pi over 2. So basically, the domain for tangent and secant looks like this. Domain is S such that S cannot equal 2n plus 1 times pi over 2.
Will the degrees for the next one be 10 over pi? Like, wait,
Yeah, sorry. Let me zoom out too. I'll explain this. Where n equals any integer. All right. So let me explain. D, your domain, so that's what that D stands for. Domain is this notation. Have you guys seen this notation before?
No.
Oh, all right. Well, let me introduce you to set notation. So S can be whatever it wants, and then this line means such that, or as long as S is not equal to 2n plus 1 times pi over 2. Hold on, Miss Savia. What? You're so making things up. All right, go back. Remember down here when I said I bet you can guess the next one? It was 1 pi, 3 pi, 5 pi, 7 pi. The next one's 9 pi, then 11 pi, right? Right? What are those numbers? What are 1, 3, 5, 7, 9? They're odds. They are integers, but they're odd integers, right? Right? Odd integers? Okay. How do I express an even number? Every even number can be written as 2 times some other number.
Yeah, you take any number.
Any number you want, and you multiply by 2. You're guaranteed to get an even number, right? So how do I get an odd?
You
2
would
plus 1.
have to plus
I do 2 times any number I want, and I just add 1 to it. That's all this is. So that's saying, okay, any number, any odd number times pi over 2.
Oh, so if like n was like 15.
Right. Then I get 31 pi over 2. And that would be a time when S, I couldn't have that value because I'd have an x equal to 0. All right. I know. It'll get better as we kind of work our way through it. So, tangent and secant, I can have any x I want as long as it's not some odd number times pi over 2. Because when I have an odd number times pi over 2, I get an x that's equal to 0. And these have 0 or x's in their denominator, so that's going to break my expression there. Okay? So, it's similar for cotangent and cosecant. If you look at those two, cotangent and cosecant. So, look at these. See how they both have y's in the denominator? So, they are not allowed to have, I can't have zeros for y. Well, where is y 0? So that's basically what I want to know for this one. Okay. Oh, wait, let me draw this line so that it includes them. Okay. So these have y in denominator. So y cannot equal 0. Where is y equal to 0?
0 degrees and 180, or 360.
Well, remember, y is sine. So I'm looking for,
You have 180 degree angle wise.
well, the first one that we hit is when sine is 0. 0 degrees. Okay, sine of 0 is 0. So where is y equal to 0? So it starts at 0 degrees, which is 0. And then you're right, 180 is the next time, and that's pi. And then I get 360, which is 2 pi. 540 is next, which is 3 pi. Well, could you guess the next one in radians?
4 pi.
Yeah, 4 pi, 5 pi, 6 pi, 7 pi. All of those are going to be ruled out. Okay, so
The degrees go down by 2 as well. Like it goes 1, 3, 5, so the next one would be 700, and instead of 40 would be 720, right? Because it goes 80, 60, 40, or 7, yeah, 8, 6, 40.
you're just adding 180 every time.
Well, that's easier.
So the domain is any s we want as long as s does not equal n times pi, where n is any integer. Okay. Ready?
I don't.
Example 1. Let's see. Find the exact values of sine negative 3 pi. What? What's so funny about that?
It's just
Remember that sine is really just equal to y. All right, negative 3 pi. Who is negative 3 pi? What's it the same as?
3 pi is the same
How many,
Options.
as everything
pick a number between 1 and 360. That'll be the answer.
180.
Or,
No.
Or, I mean, you could keep it in radians. All right.
It's gonna have to be 90.
In one whole circle, how many radians is that?
It's gonna have to be 270.
2 pi, right?
Yeah.
Okay, so let's think about it. If I'm starting here, one full circle is 2 pi, right? And I'm going in the negative direction. So 1 full circle, that's now negative 2 pi, right? Because I went in the negative direction. So negative 3 pi is going to land me where?
Half of it.
Yeah, so I'm over here.
270.
So it's
Negative.
Yes. And they're asking you for the sine, which is really the y value. What's the y value right there? 0. That's it. 0. Cosine of that same point.
So it's just 0.
That's it. It's just 0.
It's just 0. All that
Just
work-
0.
all that work is just 0. So cosine, you're looking for your s.
Your x value.
X, that's what I meant.
What would the x value be of this point right here?
180. So
Ordered coordinate plane, right?
the same value as r, which is the same. 1. No?
If it was 1, it would be over here.
Negative 1.
-1.
Oh yeah.
Right? I'm on the coordinate plane. That's -1, 0. Because the radius is always 1 in the unit circle, right? So, cosine of that is just -1. Cotangent of that thing. So, cotangent is x over y. So,
Y can't equal 0.
right. So, what does that mean this is?
That is a domain error. Ooh.
Undefined. Yeah.
That's your answer.
That's it.
Can you move the paper to the right? I need to write down the
Oh, okay. Do you all still have that paper with the circle on it? That we, well, the big circle, that's all it was. And we filled in the degrees and the radians, but we didn't do the ordered pairs yet. Do you remember the one I'm talking about? That's the one. It says fill in the blank at the top, right?
Unit circle, it's over here.
Yeah, this one.
Let's see if I can find that Larry.
So, we are going to fill in these ordered pairs as we go around. Of course they follow a pattern. So once you get the pattern down, it's relatively easy. And I'm also going to show you kind of how to quickly, the radians, there's a pattern to those too. So we'll talk about that in a minute. But this is not exactly on your reference sheet. How to fill this in is kind of on there, but it's not part of it. However, if you have this circle and it's all filled in, it will help you a lot in this section. Because there's a lot of things, if you just have it right on your chart, you just look and you're done. So what I have done in the past is I have given a quiz on this same unit circle. I give you the same one blank. You fill in all the pieces, and then I let you use that on the assessments. So if you don't know any of it, you don't get any, I mean, you don't do well on the quiz, and then you don't get to use it on the reference.
You just gotta look at it 100 times.
But there's a pattern, so I'm going to help you unlock the pattern. So first, let's fill in, yeah, you don't have one? I don't know if I'll see what I have. I may have to print more out, but did you not get one or you lost it, Rosie? Oh dear. Logan, did you not get it or you lost it? Let's see here.
There was a couple days last week.
Okay, looks like I see one. Okay, I have one.
Who needs this sucker?
Rosie and Logan. Let's see if I have another. Let's see if I have another. Not there. Not there. No, but that's my copy. Guess I'll give it up. Oh, jeez Louise.
Logan.
Thank you. Okay, so now we should be all set. I hope. Alright guys, so we have already filled in all of the degrees and all of the radians. So now we are going to spend some time and find these x and y pairs. Now, for this first one, let's just focus in on this first quadrant here. Okay? So, 30 degrees. This is x and this is y. Remember that x is just the cosine and y is just the sine. So I just need the cosine of 30 and the sine of 30. And that's right on your reference sheet. So the cosine of 30 is root 3 over 2. And the sine of 30 is just 1/2. Yeah. Now, what do you expect will be true about this point at the 45 degree?
Imagine secant. It's the same thing.
They should be the same, right? Because this really creates a square. So x and y should be the same. So x and y, so I should be able to look at sine or cosine of 45, and they are both the same. They are both root 2 over 2. And then I do the same thing for the 60 degree angle.
Sine.
Cosine is x, sine is y. So I need cosine of 60 1/2. And then the sine is root 3 over 2. Now already in this, maybe you see a pattern. I don't know. Do you notice some sort of a relationship?
They're
No?
all over 2.
Look at these two. Look at the 30 and the 60. Isn't it the same two values just swapped?
Yeah.
That's it.
And then 45 is just the same.
The same. Same.
Yeah. No.
Furthermore, there's another pattern here. You ready to watch this? Watch this. See how all these x values are something over 2? Look at that. Isn't that the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2? Look at that. Square root of 1 is just 1, so normally we don't write the square root of 1 over 2, but same idea. Square root of 1, square root of 2, square root of 3, all over 2. And then this is the same thing, it's just going the other way. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2.
Oh, that's a pattern.
That's it. Now, all these other ones are just reflections of these. So, in other words, these two, check this out. These two are going to match up. These two are going to match up. These two are going to match up. The only thing you have to do is adjust the sign. Since I'm in the second quadrant, all of my x values will be negative. But these are the same. Same. You just make all the x's negative. So really, once you have the first quadrant, you have all the others if you know how it all works. Okay? So these two are the same. So that's going to be a 1/2 root 3 over 2. These two are the same. and these two are the same. You just need to make all of the x's negative, so don't forget to do that, because that's important. Then I work the same way to get the, then I move on to quadrant 3, personally. So then, these two, let me zoom out a little bit. Huh? We did everything except the ordered pairs.
Can you zoom back in on that really quick?
I will in a second. So these two will match up, these two, and these two. So they work like closest to the axis and then on their way out, right? So these will be the same, same, same. But in quadrant 3, what's true? Everybody's negative, x's and y's, right? So the values will match up. So which one did you need? This one?
Yeah, I just wanted to break the bachelor's one.
These ones match up with what side? First side.
You could do it either way. Yep. So now down here we should have those same ones. Just make sure x's and y's are negative. And then we do the same thing for quadrant 4. So the two closest match up, then you work your way out like that. Okay, so match, match, match. And what are the signs going to be here? Y's are negative, right? And the x's should be positive. So all my y's are negative. And it's not a bad idea, now that you've gone all the way around, to just check and make sure that these, I'm sorry. Just double check that it is mirror image between quadrants 1 and 4, that it really did. You didn't mess up somewhere along the way. So that's a good kind of final check that these match up, these two. And they should. So again, if you can get quadrant 1, you can get all the other ones as long as you adjust the signs. And it's not like you have to memorize root 3 over 2 comma 1/2. I got it from here. You don't even need to memorize that cosine is x and sine is y. It's here. It's all right here. It says sine of theta equals y over r. It's just that r is 1. So now you're like, oh, okay, sine is my r value. That's 30 degrees. I need the x and y values. So you can just get it all from here. But once you know these 3, you know them all. Now, I know you're thinking, okay, Miss Sabia, I can handle the degrees and maybe these x and y coordinates don't seem so bad, but you really expect me to know all these radians? You expect me to know that this is going to be 5 pi over 6, and this is going to be 5 pi over 4, and this is 4 pi over 3? What? Yes, I do, because there's a pattern. I'm going to teach it to you. You ready? And maybe you can find it. Maybe I'll keep my mouth shut. Can you find a pattern to fill in all the radians?
3, 4, 6. 6, 4, 3. 3, 4, 6. 3, 4, 6.
I'll give you a hint. Should I give you a hint or keep my mouth shut?
It goes 6, 4, 2, 6.
I would look at just like the 45-degree angle. So look at the ones, the 45. So the 45, 135, 225, 315, the ones in the middle, and your quadrantal angles. So maybe just look at these. Can you see a pattern between 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2? Do you see a pattern there? No?
Yeah, I do. Should I?
Yeah, go ahead.
Okay, so 45 degrees is 1 pi over 4, and then 135 is 3 pi over 4, and then 225 is 5 pi over 4, and then 315 is 7 pi over 4. So it's just odd numbers.
Yes.
Odd number pi over 4 for the question.
So, you're right. I'm going to add to it a little bit. So if I start at 0, obviously 0 is 0. Okay, big deal. Now here, I have 1 pi over 4, right, at the first 45. If I go 45 more and I get to here, that's just 2 pi over 4. But Miss Savy, that doesn't say 2 pi over 4. But isn't 2 pi over 4 just pi over 2? Right, if you reduce it, right? So you just start at 0. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is just pi, right, hello, 5 pi over 4, 6 pi over 4, which also reduces, 7 pi over 4, 8 pi over 4. So, for your, you may want to jot this down, I don't know. So, for your 45, so multiples of 45 degrees are just n pi over 4. So I start at 0, and then the first one's 1, 2, 3, 4, 5. If you go every 45 degrees. Do you want me to go over that again? Did I lose anybody?
Yeah.
Okay, so starting at 0 is always 0, okay? So that, oh, hello! You're just in time for me to reiterate this pattern. So if you could get this sheet out that we filled in part of it before. We're now filling in the, well, actually, we're past that. I'm teaching you the pattern to know all the radians.
Okay.
So every 45 degrees is going to be some number times pi over 4. 0 pi over 4 is just 0, right? And then 45 is 1 pi over 4. 90 is 2 pi over 4. But what's 2 pi over 4 really? Isn't that just pi over 2? Right? Doesn't that just reduce? So then I go another 45. That's 3 pi over 4. 4 pi over 4 reduces to pi. 5 pi over 4, 6 pi over 4 reduces, 7 pi over 4, 8 pi over 4 is just 2 pi. So if you go every 45, it's just that number times pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, and so on. So that'll get you all the 45-degree angles. Now, let's look at every 30 degrees. If you go every 30 degrees, including the quadrantal angles again, see if you can find a pattern for every 30 degrees. Every 30. It's something very similar. It's just a teensy bit different for every 30 degrees.
Is it over 6?
Yes, that's it. It's just over 6 instead. So I start at 0, and then my first 30 degrees is 1 pi over 6. Then it's 2 pi over 6, but that reduces to be pi over 3. Do you see that? Everybody sees that? And then it's 3, hold on, where was I? 1 pi over 6, 2 pi over 6, 3 pi over 6. Isn't 3 pi over 6 still pi over 2? So it doesn't matter whether I hit it as I'm going through the 45s or through the 30s. It's still going to be pi over 2 no matter what. So there's 3 pi over 6. 4 pi over 6. You just reduce it. 5 pi over 6. 6 pi over 6. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. And 12 pi over 6. So every multiple of 30, it's the same thing. You're just going to do it pi over 6. multiples of 30 degrees are just n times pi over 6. So if you know that, you've unlocked this whole thing. And I assume that you all can fill in the degrees. Yes? Okay. So the degrees are straightforward. And now you can do your radians if you just practice a little bit. So every 45, you just do pi over 4. Every 30, you do pi over 6. What do you think? It's all right? Now, once you have this, all the questions that I ask you are going to be so easy, right? So if I look at this, right, it says find sine of 4 pi over 3. Well, I just find 4 pi over 3. Hey, look, there it is right there, 4 pi over 3. The sine would be what value? The x or the y? Y. So it's just negative root 3 over 2. If I have this circle filled out in front of me, that answer took me 2 seconds. Cosine of 4 pi over 3 would be it's only right there.
1/2.
Did you say negative 1/2?
Yeah, I didn't put the negative in the.
Oh gosh, you have to.
Yeah,
That's crucial.
sorry.
The next one's a little bit tougher because I don't have a negative 9 pi over 4. So I got to figure out where negative 9 pi over 4 would get me. Well, let's think about it. Negative 9 pi over 4. Change it to a mixed number for a second. Isn't that negative 2 1/4? Right? 9 over 4? I'm right here on your notes. Well, aren't I going to go around the circle in the negative directions 2 whole times and then just go pi over 4 more? You with me or no? Not so much? No, I think I lost you all. Guys, how many radians in one circle? 2 pi, right? This is just going in the negative direction. Isn't that bigger than negative 2 pi? Right? 9 over 4 is bigger than 2. Right? It's 2 1/4. So this means I have to go negative 2 pi. And now I have what's left over, negative 1/4 pi. So, wouldn't negative 1/4 pi land me right here? Right? Negative 2 pi, and then 1/4 more.
Wait, so
Why does 1/4 then be there?
Because if this is 2 pi, right? See how, well, okay, go this way. See how 1/4 pi was 45 degrees? So wouldn't negative 1/4 be negative 45 degrees? Right? Same idea. So I'm just going this way, 45. Oh, you missed that whole thing. I'm videoing though, so. You know what? Let me end this video just so we make sure we have it.